Hello everyone, in this video we are going to continue our discussion on reducible to exact differential equations, or we can say finding out integrating factors for non-exact differential equations. So far we have discussed two rules. Rule A, in which we found out integrating factors of the form x to power p, y to power q, and then rule 2, which had two versions, 2a and 2b. This is rule number 3, which is applicable to homogeneous differential equations only. So for homogeneous differential equations, suppose we want to solve a homogeneous differential equation by making it exact. We already know that homogeneous differential equations look like dy by dx equal to a function of y by x, and putting y by x as v or something, we know how to reduce it to separable and then solve it the separable way. So this is one technique of solving homogeneous differential equations. Another technique which we are going to learn in this video, which is going to be talking about integrating factor for a homogeneous non-exact differential equation. So what we are going to do in this is we are going to make the given homogeneous differential equation exact and then solve it the exact way. If it is already exact in the original form, there's no problem, we can solve it the exact way. Suppose it is not exact to begin with, then there is a rule which helps us to make homogeneous non-exact differential equations exact, and that rule is the following. Suppose the given differential equation is put in this form, m dx plus n dy equal to 0, because we know that for checking exactness, this is the preferable format in which we try putting the equation. Now suppose this is a non-exact differential equation. That means we do not have the equality of these two partial derivatives. Del m by del y is not the same as del n by del x. Suppose that's the situation and this equation is very much homogeneous. So that means the overall degree of each term here in m and n is the same. Suppose that's the situation, then an integrating factor which can help us to make it exact is 1 upon m times x plus n times y. So you multiply this function which is appearing with dx with x, add it to the product of n with y. So let me, obviously this would make sense only when mx plus ny is non-zero. Otherwise this technique will not be applicable because division by 0 is not allowed. So let us take one peculiar homogeneous differential equation and try to solve it by making it exact. So suppose this is the question given to us. We are let's say solving x square minus 3y square dx plus 2xy dy equal to 0. We already know how to solve it the homogeneous way. We can have y by x equal to v approach, because it's a homogeneous differential equation. All the terms here have overall degree 2, so it's homogeneous. This is one of the techniques which helps us to find the solution. Now suppose instead of using this technique of y by x equal to v etc. and then making it separable, suppose we are interested in checking its exactness. If it is exact, we know how to solve it. Exact differential equations, just they cannot they do not require a very lengthy procedure. It's just a one-liner, two-liner procedure which helps us to find the solution of an exact differential equation. So suppose it is exact also, then we are done. If it is non-exact, then there's a technique which helps us to make it exact. What we do is we find out mx plus ny. What is mx plus ny in this case? This is my m, this is my n. So what is m times x? It means x times x square minus 3y square. And what is n times y? It is 2xy times y. Let's simplify and hope that it's non-zero. It's x cube minus 3xy square plus 2xy square, which boils down to x cube minus xy square, and that's equal to x into x square minus y square. So this is something non-zero, and hence for this homogeneous differential equation we can have an integrating factor which is 1 upon mx plus ny. That means that if you multiply this homogeneous differential equation throughout by 1 upon x into x square minus y square, the new equation is going to become exact, and then you can solve it very easily using the exact procedure of solving differential equations, right? So let's look at the differential equation, go back to this and multiply throughout by the integrating factor. The given equation was x square minus 3y square dx. So x square minus 3y square dx plus 2xy dy equal to 0 was the given equation. Now, since I've got an integrating factor, let me multiply this by the integrating factor x square minus 3y square when multiplied with 1 upon x into x square minus y square makes it this. So this is my new m, and the new n is 2xy upon x into x square minus y square. So this is my new n. If I want, I can simplify it a little bit. I can separate the terms to write the first one as x upon x square minus y square minus 3y square upon x into x square minus y square. That's the splitted form of m. And for the n part, you can see that this x is cancelling. So we'll have 2y upon x square minus y square dy equal to 0. Now, since it was homogeneous and we tried 1 upon mx plus ny, and mx plus ny luckily turned out to be non-zero, so we could multiply by 1 upon mx plus ny. You do not have to check here that this new equation is exact. It will surely be exact. But for your own satisfaction, if you want, you can check the equality of partial derivatives and solve it to see that both the partial derivatives are matching. The new equation is indeed an exact differential equation. So since it is an exact differential equation, we know how to solve exact DEs. We integrate this m with respect to x, treating y as a constant. So let's do that. When you integrate the first term with respect to x, treating y is like a constant here. So obviously the answer would be 1 by 2 log of x square minus y square, because you will do it by substitution. You can just put x square minus y square as t. 2x dx gets adjusted in the derivative, so you divide and multiply by 2 and all that stuff. So that helps you to get the integral of the first term with respect to x, treating y as a constant, to be this. Now we need to integrate this with respect to x, treating y as a constant. So since y is a constant, 3y square is like a constant. So it's like minus 3y square waiting outside, and you just have to integrate 1 upon x, x square minus y square dx, which is very easy to integrate using partial fractions. And from here you have to take terms involving terms from n which are independent of x. Now there's no such term which is independent of x, because there's just one term. This is the single expression which is contributing to your n, and there's no term independent of x in n. So n star is basically 0. So you do not have any contribution from n here. So the final answer will be this equal to c. So it's just a matter of integrating this easy integration. If you go back to your integration rules, then it's easy to see that you can just, do partial fractions like this, and your derivative gets adjusted in this format. I've just done 1 upon x, a upon x plus b upon x square minus y square, and then you ax plus b upon x square minus y square, like that. When you do the partial fractions and you integrate with respect to x, this is what your answer looks like. So half of log of x square minus y square plus 3, because this cancels with this, it's 3 log x, and then this minus with this is cancelling, minus minus plus, and there's a minus here, so that makes it minus 3. Again the same integration is appearing here, so 3 by 2 log of x square minus y square is equal to c is the answer. Now if I want, I can combine logs, and in fact I can take here also, I can take it to be log c, so that logs can be combined to make the answer look presentable. You can see that these two terms are worth combining. Here you have a half, here you have a minus 3 by 2, so effectively you have a minus 1 log of x square minus y square is equal to log c, which can be further simplified. You can combine logs here and write it as x cube is equal to some constant of integration times this goes here to make it look like this. So where is k is the arbitrary constant of integration, so this happens to be the general solution. So you can see that you did not adopt the approach of y by x equal to v, though that could be one of the possibilities. You could have done this general solution for this differential equation by putting y by x equal to v, but this also is an alternative option that is available, and that's available only for homogeneous differential equations. So homogeneous differential equations which are non-exact to begin with can be made exact if your mx plus ny happens to be non-zero. You just multiply throughout by 1 upon mx plus ny, that serves as an integrating factor, and once you multiply by 1 upon mx plus ny, the new equation becomes exact. So you have two options available: either go for y by x equal to v, or multiply by 1 upon mx plus ny and make it exact and then solve it the exact way. So that is all about finding integrating factors for non-exact differential equations. Thank you so much for watching.